Okay, so our next speaker is Cyril Cohen from INRIA in Lyon, talking about hierarchy builder.
Thank you. So I apologize for giving this talk once again to those who already seen it, but that's fine. Sorry. I will try to okay. I'm a bit embarrassed because in a few months maybe I would have much more to say, but right now I will just comment on what is and not on what will be. So I will present Hierarchy Builder, which is a tool to build hierarchies of algebraic and not necessarily algebraic structures in the Rocq proof assistant, for now at least. And I will first put the tool in context. So the first thing is how do we represent structures in type theory? So as I can see it, there are essentially two extreme ways of representing mathematical objects. Either so they are composed of several pieces. So for example, a group is a set with a neutral element, a binary operation, a measurable space, which I will use as another example, is a space. So it's a set with a distinguished set of sets and closed under various operations. And usually, when we deal with mathematical objects, we regroup all this data and we deal it with and we name it. We call this a measurable space, not a space with this and that. So it's very natural when we talk naturally to say a group is an element of a type which represents all groups. A measurable space is an element of a type which represents all spaces. So either when you formalize math, either you represent it in several pieces or in a single piece. So if you regroup stuff, like in the first example of the definition of the polynomials over a ring, you can take a ring and it gives a ring, and it's very compact. So it leads to more conciseness to regroup things. And if you don't, then you have this kind of statements like polynomials. You can represent them in various ways. So univariate polynomials in this case, you need at least, I mean, there are several ways you could make them up, but one way is to have a test for being zero. So this is what this function is. And then in order to add them, you just need an operation. I mean, you don't even know that's addition at this stage. So not regrouping has advantages and it has also problems. But regrouping also has problems. It leads to less conciseness in other respects. For example, if you have if you see Z as a type, you can see it as a group and it's a different object. You can see it as a ring and it's again a different object. And the same for product. You have several products in every different, well, let's say category of structure you may consider. So the topic of hierarchy builder is to provide a way to declare this in a single way and get everything done for you. So that's what I'm selling right now. But first, let's go back to what is a mathematical structure, at least for hierarchy builder and for us. So the standard definition is a carrier, which is a set in set theory or a type in type theory, or maybe a set in type theory. I didn't even consider that yet. Then you need a set of constants and operations, and then axioms that talk about those constants and operations, and that make it a structure as you expect. So for example, an additive monoid is given by a carrier, which is a type, a constant 0, a binary operation, which is the addition, and 3 axioms. So I say additive because here there is I mean, it's common to name the operation and not just have a random operation. It's the addition. So for example, so I will now present many ways one could represent this with your own hands in type theory. So I used here the syntax of Rocq, but you can easily transpose to whatever dependently typed language you want. So you can say a monoid is, so I will present first the fully unbundled class representation. That's how it's called from a paper from 2011, the math classes library. And for them, a monoid is has parameters, the carrier, the operation, and the constants, and contains only the axiomatics. Then you can have another representation, which is the semi-bundled class representation, where this time the parameter is the class and the fields contain the operations and the axiomatic. Then you have another way, another issue coming up, which is now in a hierarchy of mathematical structures, the problem actually comes when you have multiple structures. So here, if I introduce group, what is a group? Is it, so I have a monoid. Is a group something that takes a monoid and adds stuff? So now you cannot quantify, and you cannot just say I'm a group, you need to say I'm a monoid, and this monoid is a group. So this is maybe unnatural, but sometimes it's good to see it like this. Another way, which is maybe, sorry, is there water around? I will continue like this. Another way to deal with the introduction of a new structure like groups is to duplicate things, except it's not really always duplication. For example, from a monoid to a group, you can actually remove one axiom. So it looks like I duplicated, and I could get something more compact by using the previous representation, but actually I'm introducing redundancy in the axiomatic. Okay, I will explain later how to deal with that. Now let's see another way to package, to represent structures. Instead of having it qualification on a type, you can put the type inside the fields of your structure. Here we call it sort. And then you get one type where its elements are essentially the monoids. But it's not exclusive with the previous representation. You can say, so you can reuse the pieces I introduced and say, okay, I can say what is a monoid, but I can also bundle it together with the type. So I call this the simplified pack class representation because, I mean, you cannot see yet, but when you have multiple structures, you need to use a more elaborate scheme. So now let's add groups in the picture, and this is called the packed class, not simplified, representation of structures. So if I want a group in the end, and I have defined monoids, so I have this is monoid record, which contains the data needed to make a type a monoid. Then I can bundle it together with the type, and I get the type of monoids. Then I can define a group as what I need to extend a monoid with to get a group. But then I can immediately package together the data of the monoids with the data of the groups, and I've got this is group record, which tells me what I need to add to a type, just a type, to get a full group. With the duplication that I mentioned earlier. And now a group is just the bundling of a type with this is group structure. So nothing new until now. It's a cold case. So there are many other possibilities, and they've all proven very tedious or really bad. I mean, like it happens that the fully bundled classes are really bad because they don't allow proper indexing. Telescopes have proven very, I mean, if you don't bundle a type with its class, then you have many inefficiencies in the usual unification algorithms. Modules from OCaml, well, they're not first class, at least in the Rocq proof assistant. So you lose the ability to freely quantify over your usual algebraic structures. And records without inference, they are really hard to use because you need to explicit all the time the proof of everything without help from the proof assistant, which makes the proof assistant not so assistant. So in the end, there have been a various number of choices made in various proof assistants. For example, Rocq MathComp, so the library I'm one of the maintainers, uses the packed class representation as of now, and it used to be the case in MathComp 1. Right now, it's a variant of what I presented. Math classes uses fully unbundled records in the logical representation. LeanMathLib uses semi-bundled records, but I didn't know there were plans to unbundle. I'm eager to learn about it, by the way. And Agda uses both. Actually, MathLib also has the option to bundle, but then you lose inference as far as I know. I mean, you don't lose it completely, but the inference is expected to work on the unbundled ones. But talking about inference, yes.
What does special case for varieties?
Well, it doesn't follow the general pattern of having fully unbundled. So there is a formalization of varieties, algebraic varieties, and it doesn't follow the general pattern. I can't remember the specifics. So I was talking about inference. All of this was only the representation as a term in the calculus that is used to formalize those objects, but it wouldn't work from the user perspective without inference. And to complete this logical representation, we had metaprogramming, and in Rocq MathComp, it's the canonical structures for now, which are used under the hood. In math classes, it's type classes. In MathLib, it's type classes. In Agda, I can't remember, and I didn't write it down, so I didn't help myself here. But it's not enough. In MathComp 1, there was also a validator to make sure that it held up together. I should have added MathComp 1 here. In math classes, there is a lot of boilerplate and hints you need to configure precisely. In MathLib, you need to add priorities. I mean, you cannot expect to find, I mean, to the instance, the type class mechanism to find the right priority for you. You have to introduce it yourself, and you need a linter to tell you whether you're wrong or right. And in Agda, you have directives to help you with juggling with various structures. So none of these are straightforward. You need expert knowledge of the checker or lint, and you need helper from the linter or additional checkers. Some encodings, especially the one in MathComp version 1, were extremely verbose. I think the encoding was quadratic in the depth of the structure, which is really bad when you have to write it as a human being. So at some point, we gave up on it. And some problems that are known from a design perspective now are sometimes detected very late, like the priority of instances, the indexing of type classes, or the more subtle forgetful inheritance property that is an invariant of both MathLib and MathComp, which you need to check for or get beaten by it. So the solution for this is hierarchy builder. It provides a domain-specific language to help you declare the structures you want to have, and it takes care of all the rest. So you don't have to specify priorities. You don't need a linter. The linter is the compiler from the domain-specific language to Rocq. If we miss something, you can add it to this compiler. And then you don't need to be an expert anymore, or maybe less of an expert to use it. So let's take a step back and remind what are hierarchies of structures for in mathematical development in formalized math. The purpose is to factor theorems in order not to repeat the lemmas you've already proven, of course. And maybe even more importantly, to find automatically the structure you're dealing with in order not to have to say, yes, I have this structure because of this, that, and that. No, when it's structural, it should be inferred automatically. So in order to have a good tool to design hierarchies of structures, you need the following. You need a way to declare new instances, a way to declare a new structure, be it above, below, in the middle of a hierarchy of structures. You need to handle diamonds. You need to be able to inherit from multiple structures. And maybe you need to amend code. Maybe you don't need to. Maybe we want to minimize the amount of code you actually want to amend, because if you have a 2 million line of code library and touch one structure at the roots, you may not want to edit all the files in your library. And you also need to provide several ways to instantiate a structure. One way is not enough. For example, in the group representation I've shown, maybe you want to omit the spurious axiom when you know you're instantiating a group. And you also need a predictability, because you don't want to end up inferring one instance in one case and another one in another case, and then you have something that look alike and it's not the same thing, and you don't know it, and you need to enter an expert debug mode or ask a question on Zulip. And finally, you wish to have robustness to a new declaration. When you add something new, you don't want to be reformatting everything, especially if it's in the middle of your hierarchy of structures. So hierarchy builder provides a domain-specific language to generate and extend a hierarchy from, let's say, minimal, well, maybe not minimal yet, but as minimal as we can inputs. And it lets you amend a hierarchy without breaking your code, or maybe it's better said, or more honest to say, it localizes the perimeter in which you actually have to edit. And past that point, you don't have to edit anymore, unless there's a bug in hierarchy builder, but we'll fix it. So hierarchy builder adopts the point of view that type theory is actually an assembly language, and that and it takes care for you of generating things in a consistent and predictable way for you, so that you don't have to do it by hand. Okay. In practice, we extend so we generate the hierarchy using the mathematical components packed class methodology. We enforce a discipline using mixins and factories that I will detail later on. And it lets you encode built-in safety measures, like the one I was talking about, so detection of overlapping instances and non-forgetful inheritance. And what I must say is we are working towards changing the actual generation target to in a way that I will explain later and that will satisfy a few of you. So what are the applications? So maybe the first big application, it was the intent of the tool. It was to make sure that the code of MathComp becomes simpler. So now it's done for a few years already. So MathComp 2.0 uses hierarchy builder to build all its hierarchies, as well as the extension of MathComp, the analysis part. And actually many other developments that I'm actually not involved in start using hierarchy builder, starting with, so this is one of the early adopters, the monadic effects and equational reasoning in Rocq library. And the fun fact is that when we ported MathComp, so we started around, well, March, April, actually, 2021. And we finished 2 weeks later, porting 140,000 lines of code, and we were only 10 people. And the this is the thing that is very satisfactory. Instead of increasing the number of lines of code, we actually managed to drastically decrease it. So it's not that obvious because we introduced also a lot of backward compatibility notations and stuff that lasted for a few versions, but we gotten rid of them now. So maybe we gained 10,000 lines of ununderstandable boilerplate thanks to this, and in a record time. And also the great news is, since we wrote the structures in a domain-specific language dedicated to this, when we are going to change the backend and make sure the compile target is different, we don't have to edit all of this. It's done now. I mean, this is the nice part. Okay. So, what does hierarchy builder do exactly? I love this example because it's the way we, I mean, actually I was introduced to math. I was introduced to structures in a very different way depending on whether we were doing algebra or analysis. For example, when doing algebra, I was, well, actually I'm lying a little bit. I was not introduced to monoid first. I don't know why, but I was introduced to group first. And then I was told that rings were actually groups, and you add a new operation and stuff, and fields, it's a ring, but you have this invertibility of non-zero elements, and so on and so forth. And when doing analysis, I was taught things the other way around. I was first introduced to norm spaces, I mean, the Euclidean spaces actually first. And then as one day a teacher said, wait, actually you have more general structures. For metric spaces, you can do more stuff. And then someone else said, wait, you have topological spaces. And way later, I learned about uniform spaces and so many different spaces I didn't imagine, but I learned the other way around. So from the proof assistant perspective, I mean, the direction of the arrow is flipped here. It's very, very strange. So, and the problem is going through the arrows must be automated. So if you start defining, I mean, you cannot change paradigm in the middle of your library because the automation should remain uniform. So here, the meaning of the arrows is always deduction, but in the first line, they represent extension. You add a thing to your structure. So of course, when you erase, you say every group is actually a monoid and so on. But it also means that you can deduce new stuff from the old one. For example, from a norm space, you can actually say, okay, I have a norm space. So the metric is given by the norm using x minus y, norm of x minus y, and I get a new operation. And the problem with this is that actually you can't divide the two worlds because they are entangled. I mean, there is no such thing as structures from calculus on one side and structures from algebra on the other side. So let's review the advantages and the problems of the two ways of seeing inheritance in structures. So on one side, I will deal with structural extensions, so from monoids to groups to rings and so on. So it's very compositional. There is no need to start from scratch all the time. You can just build your way up. It's noisy because whenever you add a new axiom, maybe you don't need 10 axioms anymore in the previous representation. So I gave the example of groups earlier, which is maybe more striking. A simpler one is the one of commutative monoids. When you add commutativity, you can remove one of the sides of constellation. And it's not robust because when you want to insert a new structure, you're destroying your pattern. I mean, you're not incrementing from, if you define, for example, field from a group and then you introduce rings, you actually don't define field anymore from rings. And so you broke the design you actually implemented. So this is non-robust to change in the code. Now, the advantages of structure entailment, which makes you think you should go that way instead, is it's flexible. You don't need to cut structure into small bits. You can just say, I have a norm space, I define a metric space, and I am done. But okay, not but yet. So it's robust because you can say this is a norm space. It will not change. It's not an extension of something that will change later. No, it's a precise definition and you don't change it. But it's not suitable for inference because it causes major breakage. So I will not detail this, but we wrote a paper about that, and many people rediscovered it by themselves over the years. So whenever you deduce new data from old data, you rapidly go in a state where sometimes you didn't define it the same way in both cases, and you don't see it, and you have to debug very hard to get the final answer. And sometimes there's a theorem saying that's actually true, and sometimes it's actually not true. And let's see the solution to that. So in hierarchy builder, we actually have a design where we use two different ingredients according to what you want to do. So extension is done through mixins, and entailment is done through factories. So mixins are the things you mix in, you add stuff to your previous structures, and factories are pieces of data you build your structures from. So this accounts for the two use cases. And we provide the following primitives in the system to help you. So you can declare a mixin, but you can also declare a factory. The difference between mixins and factory is that when you declare a factory, you need to explain how this factory actually is compiled to mixins you know, because the only basic bricks that you can make a structure of are the mixins. But you don't have to know it. You just need to make sure that from a factory, you can derive all the data you want, and you will get help from the system from there. Then you can declare a structure by saying that it's a, here I picked the example of a type, but it could also be a function or something in any. From the beginning, I only dealt with types, so I will say T is a type. And here in dependencies, you can name any mixin or factory you want, and the system will figure out it needs to package stuff from there. And then you can make new instances, and these instances can use any mixin of factory you know of to build the data. Okay. If I still have time at some point, I will give a short demo, but I don't know how much time I have left.
You have 10 more minutes.
Okay, so maybe I will not do a live demo in here. Okay, I talk too much. So I will do a static demo instead. So this is how you would declare a monoid in hierarchy builder. You say it's a mixin because for now I don't know. So I'm building a hierarchy of structures from scratch. So I have nothing yet. So I'm defining a monoid. So since I don't have anything to relate monoids to, I will just say this is a piece of data I mix in. So it's a mix in, and I name it ismonoid, and it's about a type M. And I attach to this type all this data and properties. Then monoid is a structure that packages this piece of data with the type. So it's the bundling operation I've described before. And I can define a new instance by giving, by saying, so it's ismonoid of Z, and I build it by saying on Z, I give 0, the addition I have in my library, the associativity, left and right neutrality. Okay. Simple. Now, let's say I want to add, what was it? Semi-groups. So what is a semi-group? Well, I would like to say a semi-group is something I attach to a type. So S is my type, like semi-group. Add is the only operation I want, and I want it to be associative, and I declare my structure like this. But now I had monoid. So I want to put monoid back in the picture. So I say now a monoid is a semi-group, which I extend with a 0 and 2 properties. And now I say monoid is the bundling of a type and these two pieces of data. But then I lost the ismonoid factor, the ismonoid record I had before. So I broke my, so oops, I cannot write this anymore. I lost this piece of, I lost robustness because I cannot replay this piece of code that's maybe in a file far away. So what I'm going to do is add back the ismonoid record, but this time as a factory. So this is exactly the data I had before in the mixin in my first version, but this time I changed this keyword mixin into the keyword factory. And what I must do is say, in order to recover the implementation I just gave before in terms of mixin, I need to say every ismonoid data can be compiled to is semigroup data and semigroup ismonoid data, which helps me recover the monoid structure I have. So factories, the principle is that factory cannot be, they are not primitive pieces of data. They are things that help you derive other pieces, and they can only be used when you instantiate. Actually, they can also be used when you say a structure is this and this and that, because internally, a hierarchy builder will say, oh, you gave me this factory. I know that this factory compiles to those two mixins, so I will put those two mixins in your structure instead. Okay. Another more complex example. So I gave an example from algebra. Now I will give another example from analysis. And I can define a measurable space like that. So I say that I attach to a type T the set of measurable sets, and it must be closed under a number of properties that I don't need to mention for the purpose of the talk. And then I say the structure of measurable type is, so measurable space, but I call it type because it's a type here, is the bundling of a type T and the fact that it's measurable. Now, if I want to add a new structure in between, for example, something weaker than a measurable space, but maybe an algebra of set or a ring of sets, which has less stability properties for its notion of measurable sets, I can turn it into a factory. Then in the builders section, I can compile it down to everything I redefined, and I can still write that measurable is a T and is measurable, even though the status of this piece of data changed. Okay. For example, here I introduce this new piece of data, and I decomposed. Maybe it's not that relevant. Sorry, I will jump to the next part, which is the future of hierarchy builder that is happening. While we're talking, we are working on it's a work in progress. So now imagine that I want to define measure spaces. I have the notion of measurable function. I have the notion of measure. I have the notion of measurable space, but I don't want to repeat everything. So what we will be able to do is the following. We will have this, the way we will be able to implement a measurable space is by saying that I have a type T, which I bundle with a measurable, the measurable space structure I introduced before. It needs to have a measure operator, but it's just one operator. And then this operator is a measure. So this thing here is different because, as you can notice, before I could only mention data that was attached to the type here I'm building a structure with. But now I'm attaching also data to the operator I introduced. So this is an upcoming contribution by Matteo and Enrico, and it will be very welcome. I think it will again reduce the amount of code in the MathComp library by a few thousand lines and allow to include even more things. Yes.
Like, make sure I understand, is there a typo? So your measure, is it meant to go from set T to R?
It is, there is a typo, thank you very much. Yes, so it's from set T to R and not from T to R. Thanks. Okay, another upcoming contribution that's also work in progress, and thanks to other people, is the compilation target of hierarchy builder. So from the beginning, I said hierarchy builder is compiling to the canonical structure representation, and you need to write things in this way. You need to always write R is a ring, type, so I can write things. But this is not the way people contributing to MathLib or other libraries in Rocq like to always do things. Sometimes it's just a technical incompatibility, but sometimes it's more, it's deeper than that. Sometimes you discover that something is a ring in the middle of a proof, and you don't want your library to be so tied to the fact that you have bundled the thing first. So you need to rewrite your whole context to account for the fact that now you know it's a ring in the middle of the proof, and you just want the property to apply to something which carries the structure of a ring. So it's just a type, maybe it's a bit more, but it's not a ring. And then you say, it's a ring. So by compiling, so the thing is, in hierarchy builder, we already have a notion of class of a ring. So we have both the ability to write ring type, which is the type of all rings, and ring of R, which is the fact that R can be equipped with the structure of a ring, except we could, until now, only perform the inference on the second one. But we might soon be able to also write things like this and have it work in the exact same way using the exact same inference pattern, so that we don't also get, so we could just dump the type class, the type classes for this, but it would not get the same resolution, and maybe it would be slower. So we are working very hard in making the two resolve exactly the same way and as fast as we can. Okay, so just a little bit, because I need to praise LP and Rocq LP. For me, it's a fantastic metaprogramming language. It's the initial version I didn't update because I didn't, it's very hard to keep track of the number of current line of codes, but the very first prototype that made the whole mathematical components library compile was approximately 5,000 lines of LP code. So LP is a programming language that is a Prolog-like. It has, it doesn't really have function. It has predicates and clauses, and you can store data as if it's a piece of program. And actually, you can even add a piece of program on the fly, which makes it a very, very nice language to program with. In addition to the Prolog features, it has a treatment of binders that allow you not to use De Bruijn indices or explicit name representation or substitution. You just reuse the native, the built-in notion of binder from LP, and it becomes your binders for Rocq. That's really, really comfortable to work with. You can call different kind of unifications according to your needs. And you can use the constraint handling rules system to defer tasks for later. And it's capable of representing Rocq term in a higher order abstract syntax. It's typing judgment, it's evaluation and unification. You can reprogram the unification if you want. You can reduce according to your wishes. It's very versatile. It's a plugin for Rocq, and it lets you use, so Rocq LP is a plugin for Rocq that uses LP as a metaprogramming language. And in particular, we can and we did write new commands and tactics. Thanks to it, we could declare everything we needed to make hierarchy builder produce Rocq objects as we wanted them to be. And we maintain, thanks to it, we maintain databases across files in a configurable way. For example, in order to compile mixins, factories to mixins, we have this predicate, which takes, ignore the O column, which relates factories with mixins, and the term to actually provide it's a function from the factory to the mixin that tells you how exactly you rebuild the mixin from a factory. And this is another predicate which tells you the dependencies. In order to talk about this factory, you need all those mixins. For example, the monoides group is a prerequisite so that in order to make T a monoid. Okay, so why should you use HB? I was telling you that I was going to sell you a hierarchy builder. So why should you use a hierarchy builder? Because it provides high-level commands to declare structures and instances. So in that way, you don't need to tune your type classes in a custom way. It's predictable. It takes into account the evolution of knowledge. This is a side effect of the fact that you can have both the I learn that I can generalize and I extend. You can always add a new structure and make it so that people that don't know about it can ignore it safely. So it adapts better to the knowledge the user has, because the users, they don't need to learn about uniform spaces if they just want to use norm spaces. They will apply theorems that are more general, but they can look for them, and there are factories to help them build norm spaces without ever mentioning or seeing uniform space. And it's robust to internal changes of implementation. Oh, this is more than envision. This is happening. Okay, thank you.
Other questions for Cyril? Yes.
So I guess maybe this is a more offline question, but here you're kind of taking the type theory for granted. You say it's your assembly language, but not trying to change it, basically. Would it help? Like, are there things that would be very useful to have in the assembly language to make your work in the above layers easier?
Yes. I think anonymous records and partial implementations in the Arendt style would help us remove a lot of duplication. So right now we embed the duplication. When we generate code, we generate lots of different structures. If we had a way to not generate them, but use them on the fly, it would make the generation easier and shorter, even though it's not strictly necessary. What other features? Well, there are features we are not using yet, but that are already in Rocq, like the definitionally proof irrelevant propositions. It would be a huge bonus for the axiomatic parts of the algebraic structures, because right now we detect, so non-forgetful inheritance is when you have inheritance that does not only erase fields. So it creates data instead of just deleting data. When we recreate propositions right now for safety measures, we still flag this as non-forgetful, just because we're working with prop, and it could happen that the proof is different. Propositionally, of course, we don't care, but definitionally it's different. And with SPROP, we could just say, oh, it's safe to create new proofs, because when we will compare them, they will just be the same.
So I wonder, would other systems such as Lean benefit from something like Hierarchy Builder? How much work would it be to build this? How much work would it be to maintain or to adopt, say, math literature? Do you have any opinions here?
We tried. We only tried during 2 weeks and with other occupations, but it's. I think Lean would benefit a lot from hierarchy builder or something like hierarchy builder, because it would help write once the structure you want. And then if you want to unbundle more in the internal representation, you change the tool, like the hierarchy builder like tool, to produce a different packaging, and you don't have to edit the whole library to perform the repackaging everywhere. Because when you write your own classes, you actually say, this is the internal representation in CIC, while with hierarchy builder, you see, this is the representation as I see it. The tool will decide which bundling, which components of the system, which meta program to use.
Another question, yeah.
Yeah. I guess this is more about potential ways you could modify the type theory, but I'm specifically thinking about going from like the very bundled records to the indexed ones. There's this feature called like record patching. It's with like extension types that it's a bit obscure. I think it's in like CoolTT and maybe one of them existed, but it's to do with that kind of thing. Would that sort of thing be useful here, or is there other ways to avoid that?
That was exactly what I was mentioning before. I guess, I don't know which of CoolTT and Arendt did it first, but it's the feature that Arendt names partial implementations.
Oh, okay. So that's the same thing.
I have this record, and I say those fields will get this value. So it's like saying it's a sigma type with a definitional equality, or anonymous record with less fields and more substitutions. Yeah, and it would definitely help compiling to a different representation in a more intelligible way, but it doesn't change the principle of the tool. Right? Perhaps it will make it faster.
Okay, so thanks, Cyril. Julie.